Chapter 6, Section 1, How Enzymes Work. As you see here in this figure above my head, you have the globular protein that we think of as an enzyme. That enzyme is going to have what is referred to as an active site, shown here in red. This is going to be a pocket. You saw me in Section 1, I used my fist in the intro lecture, and in the Section 6.1 lecture, use my fist. This is the globular protein. There's going to be a fold, some sort of a pocket. That's where the work happens. That is the active site, okay? This is going to be a microenvironment based on what R groups are there. Not R groups from the substrate, R groups from the amino acids that form the secondary structure, the tertiary structure of that same enzyme. Those R groups. Remember, we separated out the amino acids by group: hydrophobic, hydrophilic, acidic, basic, positively charged, negatively charged. Those attributes accumulate and they will give that active site right there a microenvironment. So it could be wet, lots of water, and a slight acidic environment around the protein. But in that active site, hydrophobic or, slightly hydrophilic, but, negatively charged, or basic, or whatever. In chemistry course, Gen Chems and whatever, you have discussed reactions in the terms of reactants and products. Well, reactants and products are a thing, the reactants you add to the test tube to the beaker, they react together and they give you the product. It's different here in biology, biochemistry. So when we're dealing with enzymes, instead of reactants, because the term reactants means they're going to react themselves. No, we want to discuss things based on from the enzymatic standpoint, so we use the term substrate. An enzyme takes a substrate, turns it into the product by cut, paste, twist, tweaking the substrate and giving you, ultimately, a product. You look here at equation 6.1 from the chapter. E, enzyme, S, substrate. The enzyme and the substrate have to interact in that active site. So you're going to have some form of an interaction. Hydrophobic interaction with the R groups based on that microenvironment, ionic interactions, whatever. So you actually have this intermediate thing. The enzyme and the substrate are now one. Once they have interacted, you have those hydrogen bonds, those ionic interactions, whatever. There's going to be stressing and altering of bonds, the cut, the paste, the twist, the tweak, whatever. And you have this enzyme now product structure. You're going to have this transition from ES to EP. Well, the P, the product, doesn't have the correct shape. Doesn't have the correct shape to interact with the R groups. Doesn't have the correct shape to be in that active site, so it's going to be expelled. ES ultimately gives us E and P, product. Now, under normal conditions, everything that an enzyme does can happen on itself, okay? Just like it does in the test tube, the beaker, whatever. You start off with some substrates. By their own, they can ultimately become the product. You've seen this in other classes. You have a certain amount of free energy in that substrate, inherent in the bonds, the chemical bonds. Well, to get that transition from S and become P, you have to get this amount of energy increased within the mix, okay? Because it takes energy to stress, to break bonds, to reform bonds. So you have this amount of energy that has to accumulate. Things will be cut, pasted, twist, tweaked on their own, and then ultimately you end up with the product. To go this increase in delta G, and you see this little weird, almost cruciform cross-looking thing, that's to denote transition state. To go from S to P, there's this transition state. Bonds remade, bonds stressed, bonds broken. So you have this increase in delta G within the system, and then product made. And you have delta G naught, the prime naught. This is the delta G that is now been released, because this, since P is at a lower free energy state than S, this means this was an exergonic reaction. So that change in S to P levels of free energy, that is the delta G prime naught. Well, look at this big hump. That big hump that has to take place if you just added a bunch of substrate or reactants into a test tube, into a beaker on their own. That delta prime G prime naught that I said, that's the standard free energy change in a biochemical system. Since it's a loss here, boom to boom, it's lower exergonic. If P was actually up here, so the product is actually at a higher state, well, that would have been an endergonic reaction. Since it's less exergonic, if it was higher, endergonic. And you've seen it in previous biology courses when we're talking reactions. This hump here that we're talking this transition state around, that is actually referred to as the activation energy. This is the energy that's needed to put the substrates or the reactants into a transition state. Bonds are stressed. Bonds are ready to be broken, reformed. When you have the enzyme there, you see that the activation energy for this transition state is actually going to be much, much lower, because the enzyme is giving a hospitable site. The active site is hospitable for whatever that reaction is going to be. The changes in the shape of the enzyme are going to aid in the breaking of bonds, the stressing and breaking. It's going to be aid in the reforming of bonds. So you look here, you have delta G transition uncatalyzed, delta G transition catalyzed. Add the substrate to a beaker of water on its own, yeah, it will go through this transition state on its own and form product. It's just there's more free energy has to be accumulated. The activation has to be much, much higher. An enzyme on its own, much lower. But we also see, if you think back to a couple of slides ago, that E plus S gives you ES, gives you EP, ultimately gives you E plus P. Well, the E and the S, the ES and the EP, those transition states also have their own levels of activation energy. But if you look at this, none of these humps are anywhere as high in their requirement for the delta G, the free energy, as if it was uncatalyzed. Now, to go substrate to product, well, it means that there's also a mechanism for going product back to substrate. Just usually, ultimately, products are utilized by other metabolic processes before an enzyme can do the reverse. Enzymes are not magical. They do not make something happen that won't happen on its own. Remember at the beginning of this chapter, I said they just, increase the rate at what things can occur instead of a time frame of minutes to hours, hours to days, days to weeks, weeks to months, months to years. Our time frame now is minutes to seconds, seconds to milliseconds to microseconds. It speeds up the process. Thankfully, enzymes are not used up in the process. They're not a one and done thing. Enzymes are there. They continue to work. As long as there's substrate, they will continue to take the substrate and turn it into product. So these intermediates, these intermediate transition states, we're going to focus on here. The ES, the EP. Since there is a molecular interaction between the enzyme and the substrate, the enzyme and the product here at ES and EP, via hydrogen bonds, ionic interactions, and the whatnot, we see that it is not one smooth thing occurring. There is an activation energy when the substrate and the enzyme come into contact with each other, which gives us ultimately an intermediate, ES. The ES has to accumulate some energy so it can transition from ES to EP, and then there's an accumulation of energy where the enzyme releases the product. We have to take into account that there's going to be a rate limiting step, a step in this E plus S to ES to EP to E plus P, that there's going to be steps in there that are rate limiting in how much energy is required. If you look at this figure here, these step go from ES to EP has the higher delta G requirement compared to the other two steps. So this is the rate limiting step. In other reactions that could be graphed out, it could be something more along the lines of, S to ES to EP, and then like that. When this right there would then be the rate limiting step, because that interaction from E plus S to ES, turns out there's more energy needed there than elsewhere. Or it could be something along the lines where we follow this up, down, and then here a really big. Well, to go from EP to E plus P to get that release of the product, that would be the rate limiting step because the delta G requirement there is much higher than everything else. We see, thanks to evolution, billions of years of evolution, enzymes have slowly developed, evolved. Selective pressures have pushed for this development of enzymes that have lower activation energies. They're going to happen faster, they're going to happen more efficiently, and then any type of outside energy that must be put into the system is going to be greatly reduced, making that energy available elsewhere. Now, it's not a one and done. Got to remember, it's just evolution isn't a, ooh, look, this is good, but this is so much better. It's, this is good, that's better. Fast forward, 100,000 generations, this is a little bit better. Fast forward another 100 to 1,000 generations, that's a little bit better. And that, and then that, and then that, and then that. And then when you go and you look at and compare over 1,000,000 years, which is the time frame for evolution, you've made that big leap. Now, when you look at equilibrium, okay, as chemists, we always want to look at the equilibrium. We want to see what does it take, to get to the point of equilibrium. What happens if these reactions reach equilibrium? Well, here we're going to look at it and reference it as delta G prime naught. Okay, the standard free energy change. Okay, what happens if we reach equilibrium? And we're going to reference it in the terms of delta G prime naught. Just like the reaction rate, we're going to reference it to delta G transition. And that's what I'm just going to call that cruciform or cross-looking thing, transition. As always, KEQ, this is our equilibrium constant, throwing in a prime there because we're looking at enzymatic rates. So K prime EQ, KEQ, the equilibrium, product over substrate. If it's greater than 1, it means we're going through very quickly. If it's less than 1, that means the denominator is much higher than the numerator, then there's a rate limiting step somewhere in there that we have more substrate than we have product. Thermodynamically, delta G prime naught equals negative RT, our constant, times temperature, times the natural log of concentration of P over the concentration of S, which we see here. What's that mean in the real world? Well, if the equilibrium constant is extremely small, so 10 to the negative 6, that's 0.000001, way under 1. Turns out, if you do the calculations for that, delta G naught prime is way positive. And hopefully you remember back from your biology or your 244 that if delta G is positive, that's an endergonic reaction, and the chances of being spontaneous, not happening. Delta G is negative, below 0, it's an exergonic reaction, and there's a really good chance that that reaction can happen spontaneously. Well, if we look at KEQ, K prime EQ, very small number, 10 to the minus 6, very, very high delta G prime naught. Very large number, 10 to the third, so at the 1,000, delta G, negative 17. So we take this a step further. Rate constant, K, for a unimolar reaction, S to P, gives us a rate equation that expresses the rate as the velocity, or the rate, is equal to some constant times the concentration of S. Okay. What does that mean? Okay. Well, let's discuss this in the terms of first and second order reactions. First order reaction is you have S. S is all anything depends on. One S. One substrate, and one enzyme. K is a reciprocal of time. So it's actually, if you were to put it out, it would be 1 over S seconds. If you were also do that V equals KS, and you actually have two substrates, Well, that's second order. So it's substrate 1 plus substrate 1. Enzymatic reaction gives you a product. Excuse me. A plus B, enzymatic reaction gives you C, one product. Well, here our K is going to be different. Here K is going to be moles per second. Our V, velocity, is K times the concentration of S1, S2, R2 substrates. Oh. But what's that K? Oh my God. K. K is the bane of biochemistry resistance here in this course because there's so many Ks. So our lowercase k without a K1, K2, K alpha, K beta, whatever, 1, K1, K negative 1, whatever, that we saw, V, here, this is the K that you see in V equals K S, our single order, our first order reaction. That K, that constant, is actually this right here. These K's, which are different, even though they're lowercase k's, this is the Boltzmann's constant, and H is Planck's constant. Boltzmann times temperature divided by Planck times e to the negative delta G transition RT. Oh, that's pretty thick. But if you look at it though, if I get rid of all of this that I just put there, so you just look at, and you think back to our delta G equals negative RT times the natural log of P over S, our KEQ. RT, delta G of the transition state, not delta G of the entire that we saw before. But instead of a natural log, you now see E. Here's our T again. So we start to see that there is quite a bit of association, quite a bit of intermingling of these different concepts. They do start to overlap a bit. And as I've said in lectures before when I have discussed these in this course and many other courses, for a lot of these, the problem becomes figuring out which K this is. Is it this K or is it this K? What's this H? Which delta G is this? You start figuring out and you look at and you just plug in the numbers. Ultimately, what we see is that enzymes enhance rates. Look, 10 to the 5th, 10 to the 14th, 10 to the 17th. Okay, this isn't, oh, it's 14 times better, that's 5 times better. No, that's 10 to the 5th. That's 1 with 5 zeros. 10,000. Cyclophyllin catalyzes its reaction. The reaction that would take place on its own, this just makes it happen 10,000 times faster. Urease catalyzes the breakdown of urea. Okay, urea will break down all on its own. But in the presence of the enzyme urease, it happens 1 with 14 zeros. So that's what? 10 trillion times faster? Or it doesn't even have zeros there. It just happens that much faster because the urea is that stable of a compound. That's why we like enzymes. That's why all living things on this planet are based around what enzymes can do for our cells. 100 trillion times faster, a quadrillion, 1,000 quadrillion times faster. Yeah, that's time for Chapter 2, Section 2, Lecture B. We can work with. Now, when you look at that interaction between the enzymes and the substrates in that active site, you're going to see this non-covalent, as I told you, hydrogen bondings, ionic bonds, whatever, hydrogen bonds, ionic, hydrophobic effects. There's going to be some energy involved there. If there's always some energy involved, you know we have to have a Gibbs free energy constant, delta GB. Delta GB tells us the amount of energy, the amount of what is going on in this interaction between the enzyme and the substrate. The E plus S to the ES to the EP to the E plus P. This delta GB is what actually lowers that activation energy requirement. I've used this analogy in my classes, with my freshman biology students. This idea of a lock and key. That the active site is such a shape that only the enzyme is able to bind and interact in such a way in that. Kind of like, a key and a lock, okay? If you look at your keys have ridges, they have, different valleys cut out and things like that, so that when you put it in the lock, only certain thing with the ridges fits in, and then when you turn it, those teeth on the key are such a way that they move tumblers. Only the correct shaped key can not only fit in, but be able to turn. That's actually not a really good analogy, because that tells you that the enzyme is of such a rigid shape, and we know proteins aren't rigid. I mean, we do know. You look here with tetrahydrofolate and this enzyme that it's acting as a cofactor with. NADP can fit into the active site right here, as we see here. It fits in, and it is of the correct shape that we get different R groups start to interact. As more R groups interact, the shape of the enzyme is going to change. So it's not this rigid, lock and key thing. There's a little bit more complexity to it. I mean, because if you look at it on its own, the delta G uncatalyzed, some substrate is going to slowly over time, minutes, hours, days, weeks, months, years, whatever, is going to accumulate enough energy that it's going to, on its own, put itself in a transition state where, as you see here, bonds within the molecule, within the substrate, get stressed, strained, and will break, ultimately giving you the product. If the enzyme was truly the lock and key analogy, where the lock is truly rigid and does not change, is immalleable, yeah, the key or the substrate could enter in and interact, but there's not going to be any stressing and straining. Yes, there's going to be the ES formed, because the R groups are going to interact, but there's not going to be any bending. So you're going to end up with few, if any, product. Better way to think of this is you have the enzyme, has an active site that is of such a shape that the substrate can enter in, and the substrate has to be of such a shape that it will begin to interact with R groups. Not all of them all at once, but enough of them so that the changes in shape of the enzyme will stress and strain, putting the substrate into a transition state, ultimately breaking and reforming, cut, paste, twist, tweak, remember, giving us the product. So yes, you have the substrate, active site, substrate goes in, and it's not a complete interaction all at once. It's a slow interaction of different parts, different R groups, and as the enzyme changes shape. So it goes from this, starts off at this, and it goes and changes somehow. This brings more R groups into a interaction, and then the process, the substrate, we go into transition states, ultimately cut, paste, twist, tweak, giving us product. So this binding energy, this interaction, to have those R groups interacting is what's going to allow for this lowered activation energy requirement. Weak bonding, weak interactions, you're going to have a much higher activation energy requirement. It's kind of an inverse thing. Better GB, more favorable, lower activation energy. Not a quite favorable GB, more activation energy is going to have to be accumulated. The active site of an enzyme has been optimized. Okay, remember that slow, evolutionarily, a little bit better, a little bit better, a little bit better, a little bit better over thousands and thousands and thousands of generations, millions and millions of years. Optimized. So that this transition state will occur due to positioning, due to interactions with R groups. The enzyme specificity, as we ultimately see, is due to who can fit in, who can start the interactions with the R groups. That's where specificity. The better the specificity, the better the interactions, the start of those interactions, the more favorable the binding energy, the delta GB, is going to be. This reaction, that delta G transition, how much energy is in the molecules? Not, high entropy, low entropy. It's gonna, who gets in, who's able to get in, how often, how quickly, things like that. The solvation shell, that hydration shell, salvation shell, hydration shell, however you want to think of it. This is also going to have to be taken into account when it comes to this transition state, the barrier, who is and who cannot. What degree are you cutting, pasting, twisting, tweaking? A slight tweak, slight twist. You're just changing, around a chiral center. You're taking a hydroxyl from C2 and moving it to C3. Minor reactions. Well, things like this will be taken into account. Well, if you want to increase the rate, well, lower entropy, lower, just how random things will be. Binding energy is a great way to constrain this. How things bound, when things are bound, where they are bound. All must be factored into the delta GB. I mean, if your reaction is a second order reaction, you have two substrates, and you want to take two substrates and turn them here into one, well, this is going to be slow compared to, hey, you know what? I'm just going to take a first order, where I take this, and you know what? I'm going to make it cyclic. Or the same thing here. I'm going to take this, and I'm going to make it cyclic. Oh, rate enhancement, 1. Yes, it makes it happen, but it's not overly fast compared to 10 to the 5th, 10 to the 8th. So substrate's in cytoplasm. So it's in an aqueous solution. You want to increase, the rate, make a more favorable delta GB. Well, get it out of solution. Replacement of the solvation shell of destructured water around the substrate. Replace the water that's interacting with the thing in solution. Replace that water interaction, because remember there's going to be hydrogen bonds from the oxygen and the hydrogen of water with whatever is on the substrate. Replace those interactions with weak bonds between the substrate and the enzyme. So basically, you're pushing the water away from the substrate in the active site, increasing interactions with those R groups, which was what I've been saying over the past few slides. So this distortion of the substrate, once it's in the active site and starts interacting more and more with R groups, you're going to see the substrate is going to undergo distortion, also referred to as electron redistribution. There's going to be some focused redox reactions on different atoms within the molecule or whatever the substrate happens to be. You're going to be moving the electrons, moving hydrogens around in it. They're still attached to the substrate, but you're moving them around to increase affinity, hydrogen bonding with the R groups of the enzyme. So you ultimately end up with what is called the induced fit. Substrate, the product, active site, substrate gets in, starts interacting, water gets excluded, more and more hydrogen bonding, and you start to see the enzyme change shape. Induced fit. As it's changing shape, it is now also allowing for more and more R groups within that active site to interact with the substrate. So you get more and more, this tighter bond, this tighter interaction as you go from E plus S to ES. This enhances the catalytic event. Once you have this induced fit occurring, well, guess what? Catalysis. The reaction will be sparked. ES to EP. Bonds stressed, bonds broken, bonds formed. A plus B, boom, bound together, giving you product C. That's when, acid base, some of the amino acids are acidic, some are basic. Maybe within the substrate. Substrate itself is a polypeptide or some form of a peptide chain, or some organic molecule that has slight acidic properties, slight basic properties, whatever. Covalent interactions are going to be bent, twist, tweaked, allowing for other bonds within the substrate to be bent, twisted, tweaked, broken, reformed. And we're going to see that to get things to occur, maybe it is a specific acid-base catalysis where you have hydronium and hydroxyl radicals. Here they're showing, two products. Don't know what they are because I don't know what the R groups are, R1, R2, R3. But you just see here, they're in the active site. The electron here to the carbonyl there. What's occurring? Well, the oxygen here is giving up an electron to this oxygen here, which means it now has an opening in its valence shell, and this bond here can now be formed. Okay. Protons can also, in the process of this, be moved around, be transferred. So what was NH with an R4 group, hydrogen added, hydrogen bonded, hydrogen moved. You now have NH2. Things moved, things cut, things tweaked. This can now be cut, released, and you end up with this. All of this is general acid base. Who's got the hydrogen? Where did it go? Where's the electron come from? Where did it end up? Well, remember, you have amino acids. Glutamine, asparagine, lysine, arginine, cysteine, histidine, serine, tyrosine, hydroxyl, NH2, SH, NH, hydroxyl, where a hydrogen can be released. And hey, look, there's the acceptors. Who's going to take it in that enzymatic reaction? And keep in mind, all of this isn't happening, everything we've talked about in previous chapters up till now, as we're talking about the isoelectric point, the K1, K2, blah, blah, blah. We've been talking about this in a test tube. Well, this is happening in the cell, not only in the cell and the cytoplasm, it's happening in the microenvironment of the active site. Carboxyl here is going to release hydrogen. Well, guess what? There's going to be another carboxyl somewhere that's going to take it up. And there's also going to be some form of covalent catalysis, okay? Covalent bonds need to be made, need to be broken. Hydrolysis. AB, going to be cut, pasted, twist, tweaked, resulting in A plus B. Or AB plus some organic molecule X, AX plus B, A plus X plus B. All of these things can occur. All bonds, hydrogen bonds, ionic bonds, even the covalent bonds, can be made, can be broken, can be reformed during these enzymatic reactions. A lot of times it's going to be in the presence of metals. Metals, the transition state of metals. Are they taking up a hydrogen? Are they taking up an electron? Are they giving up an electron?